Okay, so if I'm not mistaken, we left off on let's see, today's Wednesday, right? So we left off on Monday, finishing up the 4-resistor bias circuit for NMOS transistors with channel length modulation effects included. Does that sound about right? Okay. So the first thing that we're going to talk about today then is the self-biasing network. For NMOS transistors. And we're going to start without channel length modulation. So the self-biasing network looks like this. We have our power supply. We have some resistance RD. And then we're going to have feedback effectively between our gate and drain. Consisting of some resistance R sub G. And we're also potentially going to have some source resistance RS down here. And let's see. I'm going to identify my terminals just so we're all on the same page. So this is our gate, drain, and source. So our potential quantities of interest here are VDS. We need to know what that is so that we can make sure we're operating the way that we think we're operating. Here is our voltage VGS. And here is our drain current ID. So let's start with something. Assuming VDD is high enough to where VGS winds up being greater than VT8. So assuming this device is on, what is literally the only operational mode it can have? Saturation, exactly right. Would you care to explain why, Logan?
I don't remember, but I know it's because of the feedback between the gate and the drain.
Okay, so we have established that no gate current can flow in this device, right? No DC gate current anyway, which means there is no voltage drop over the resistor RG. So the potential at the drain terminal and the potential at the gate terminal are the same. Therefore, VGS is exactly equal to VDS, which means VDS will always be greater than VGS minus the threshold voltage, since VDS and VGS are the same. Right. So the first step here in our analysis of this circuit is recognizing that VDS is exactly equal to VGS, meaning that we are always in saturation for VGS greater than or equal to VTH. Absolutely possible to turn this thing off, but if it's on, it's operating in saturation mode. So since we have saturation mode operation, we know that our drain current ID will be 1/2 KN VGS minus VTH quantity squared. Donald, do I need to tell you what a subscript is? GS. VGS is greater than or equal to VTH. I'll rewrite that so it's easier to see it. My apologies. Don't know why my nose is itching so much. All right, so we should be able to pretty easily come up with a KVL equation that's going to allow us to solve for VGS, right? Let me scroll up here a little bit. So if we look at the right-hand side of this guy, we can see that VDD, our power supply voltage, is going to be the voltage drop, or it's going to be equal to the voltage drop over RD, plus VDS, which is exactly equal to VGS, plus the voltage drop over RS. Since RD and RS both have a current of ID flowing through them, this gives us VGS is equal to VDD minus RD plus RS times ID. And we can use a little bit of algebra to rearrange and find that ID is equal to VDD minus VGS over RD plus RS. And we now have two equations for ID, so we can just set those guys equal to each other. And in doing so, we get 1/2 Kn RD plus RS multiplied by VGS squared minus twice VGS VTH plus VTH squared minus VDD minus VGS is equal to 0. And we can rearrange this guy. And we get 1/2 Kn RD plus RS times VGS squared plus 1 minus Kn RD plus RS times VTH. That quantity multiplied by VGS plus 1/2 Kn RD plus RS VTH squared minus VDD is equal to 0, where we obviously have another polynomial function, right? A second order polynomial in VGS. There will be two solutions, one of which will always give us a value of VGS that is negative, meaning that the device is operating in cutoff. Since these equations were derived for saturation region operation, that's obviously incorrect. The second solution is VGS is equal to VTH minus 1 over K sub n RD plus RS plus the square root of 1 over Kn RD plus RS quantity squared plus twice VDD minus VTH all over Kn RD plus RS. Obviously, we can use this equation to solve for VGS, plug this VGS value into our equation for ID, and then we have our operating point for our circuit. So let's do just that for the following circuit. Let's say that we have a 1.8 volt supply voltage, a 2 kilo ohm drain resistance, I might have to make this thing a little smaller than I wanted to. $500 ohm source resistance, and our gate feedback resistor, let's say it's a 20 kilo ohm resistor. Like so. And we want to determine our operating point, which will be VGS and ID, where say Kn is 1 milliamp per volt squared. And let's see what else. VTH is 0.4 volts, and lambda is equal to 0, so that we're neglecting the effects of channel length modulation. So obviously, literally all we're going to do is plug these parameters and these parameters into this equation. So take 2 minutes to figure out how to make your calculator do that. One easy thing to do here, if you were trying to do this calculation quickly, would be to save the quantity Kn times Rd plus Rs as a single variable in your calculator. One times 10 to the minus 3, which is Kn, multiplied by Rd plus Rs, which is 2500. Let's store that for the sake of argument with X. So that we have 0.4 minus 1 over X plus square root of 1 over X squared plus 2 times VDD minus VTH. So 1.8 minus 1.4 looks like 1.4. I get 1.131 volts, which is exactly what I got using MathCAD. Anybody else verify that? From here, we can plug in this value of VGS into our ID equation. So just to reiterate, because we're in saturation, ID is going to be 1/2 Kn VGS minus VTH quantity squared. And we should get an answer of 267.452 microamperes. Verify that for me if you want. Andrew, you got a question? VTH is the threshold voltage, 0.4 volts, given right here. All right, so I hope it's obvious. We do not need to do or set up a system of equations or anything for triode region operation because this circuit is literally incapable of operating in that mode. So our next step here is going to be reanalyzing this circuit with channel length modulation effects present. Okay. Now, this isn't going to be particularly difficult analysis because it's literally this exact same analysis, except that we now have a channel length modulation coefficient in the mix. So we know that with channel length modulation coefficients present, so with CLM, VDS is still exactly equal to VDS for sure. ID, our drain current, is going to be 1/2 KN VGS minus VTH squared times 1 plus lambda VGS, or I'm just choosing to use the equivalence of VDS and VGS to express everything in terms of a single variable. We know from our KVL equation that we used previously that VDD minus VGS divided by RD plus RS is equal to ID. And we can rearrange this guy and find that VGS will be equal to VDD minus 1/2 KN RD plus RS times VGS minus VTH squared times 1 plus lambda VGS. That's our equation that we use to solve this. Now, obviously, this is a third order polynomial. So unfortunately, we can't use our quadratic equation to give us a closed form solution of this guy that's trivial to find, but only one of the 3 solutions will actually be a positive number. So obviously, that's the one that's correct, because for any of the negative valued solutions, VGS would be less than VTH, which implies that those are cutoff regions. I think your numerical solver on your calculators should be able to solve this 3rd degree polynomial equation. Make sure your guess value is positive, and you should be good to go. I would say +1, just so that it's guaranteed to be closer to whatever it is in case there's a small negative solution. So these are our 2 different biasing circuits. You might see similar looking biasing circuits where some of the resistors are neglected. So effectively, those resistors are replaced by short circuits. Obviously, to analyze those type of circuits, you could literally use these with just those resistor values set to 0, and then whatever falls out, falls out. So these are the 2 that I expect you to know how to do. You are going to have an equation sheet for the exam, but anyway. All right, so that's our NMOS biasing schemes. So let's talk about PMOS transistors for a little bit, if that's okay. We are not going to go through a huge derivation of the behavior of PMOS transistors because for the most part, they behave in the exact same way as an NMOS transistor. We just need to swap the subscripts for our device. So generically speaking, the schematic symbol that we are going to use for PMOS transistors is going to look like this. This is our source. This is our gate. This is our drain. So the source is at the location of highest potential. And typically speaking, for CMOS devices or integrated circuit devices, the body is tied to the source terminal. So the body is also at the highest potential in the whole thing. We're going to have a controlling voltage then VSG that determines how much current flows through the device. Our current ID is still going to flow down. It's going to flow from the source to the drain, but we're still going to call it a drain current. So the current is still flowing from the position of highest electrical potential to the position of lowest electrical potential through the transistor. In this case, its holes are being moved from the source area to the drain area. So we're following positive charge transfer, which is why the current is pointing in the same direction as the charge carrier moving, because we're dealing with positive quantities. And then we are going to have a voltage, VSD, that tells us whether or not we are in triode region operation or cutoff operation, okay? So let me just describe these regions for you. In the cutoff region, VSG is less than or equal to the absolute value of VTH. So I want to talk about this real quick. For whatever reason, it has been decided that the threshold voltage for PMOS transistors is typically described as a negative voltage. I believe this is because we need the gate to be 1 VTH lower than VS or more for this guy to turn on. So we're going to be stuck with a bunch of absolute value signs here. In practice, if you just read the threshold voltage for a PMOS transistor as a positive quantity, you can throw away all these absolute value signs. They mean next to nothing. We're just working on the understanding that the gate needs to be lower potential than the source in order to turn this guy on. Okay. For triode region operation, we need VSG to be greater than or equal to VTH. So effectively, we have to turn the device on, establish a channel, and then also we want our source drain voltage, VSD, to be less than VSG minus the absolute value of VTH. In this region, our drain current is given by mu P Cox W over L VSG minus the absolute value of VTH times VSD minus 1/2 VSD quantity squared. I just want to point something out here. Literally, the only difference that we have for triode for NMOS and triode for PMOS is that we have swapped the order of the subscripts on all of our voltages. We're using absolute value sign for our threshold voltage because for whatever asinine reason, it's given to us as a negative value instead of a positive value, which I can't really figure out. And then we're using hole mobility because that's the charge carrier that's actually being transferred from the source to the drain. So it's really the exact same equation under the exact same set of constraints. Just flip the subscripts and use a positive value for VTH. For saturation, we again need to have the transistor turned on, so that's VSG greater than the absolute value of VTH. And we need the quantity VSD to be greater than or equal to our overdrive voltage of VSG minus the absolute value of VTH. And our drain current is 1/2 mu P Cox W over L VSG minus the absolute value of VTH quantity squared. And when channel length modulation effects are present, we'll have 1 plus lambda VSD. So these are our equations for a PMOS transistor. Again, it works in the exact same way. Saturation means that pinch off has occurred. We need an electric field in order to move our positively charged holes from the source region of the device to the drain region of the device. Literally everything is the same, except we have to swap all of these things. Luke.
The last variable DS or ST or ST?
This guy right here, SD. So the channel length modulation term is always dependent on the drain source voltage. For a PMOS, it's VSD. For an NMOS, it's VDS. So effectively, this is telling us how much we've pinched off our channel. So it's dependent on VSD. All right, so we can develop bias equations for PMOS circuits as well. The 4 resistor bias network, the derivation is going to be extremely similar to what we did with the 4 resistor bias NMOS network, but we're going to see a few subtle differences beyond simply flopping or switching the subscripts and using absolute values every time we see VTH. For the self-biasing circuit, it is literally the exact same relationship, except that you swap the subscripts and use an absolute value. Okay. So let's look at PMOS 4 resistor biasing network. We'll do it first without channel length modulation. And so it's going to look something like this. Our resistor R1, our resistor R2. This is going to be our resistor RS. Here's our PMOS transistor. Here is our resistor RD. This is our voltage VDD. Let's see. This is obviously our gate terminal, our source terminal, our drain terminal. This is our voltage VSG. Here is our drain current ID. Here is our voltage VSD. Like so. So we'll start by assuming that A, the device is on, and B, it's on and operating in the saturation region. We can easily see that VG is equal to VDD times R2 over R1 plus R2. So our equation for our gate voltage literally doesn't change at all. If we do, I'm going to draw a line here to tell you kind of where we're doing things. So we're going to do KVL around this loop. Okay. So we can say that VDD, the power supply voltage, is the voltage drop over our resistor RS plus the quantity VSG plus the quantity VG. So it's going to be ID times RS plus VSG plus VG. I'm going to do a little bit of mathematical manipulation here. So I can say that VDD minus VG, so I'm going to call this guy VDD R2 over R1 plus R2 is equal to ID times RS plus VSG. Let's look at this guy portion right here. Okay. So this is one of the things that's going to be a little bit different than what we saw for our NMOS transistors. So we could multiply this first term by a factor of R1 plus R2 over R1 plus R2 to be able to combine those two things together, right? What that would give us is VDD times R1 plus R2 minus R2. So the R2s go away and we wind up getting VDD times R1 over R1 plus R2. So in our NMOS equations, we were finding, or we wound up using, sorry, let me scroll up here, the voltage drop over resistor R2 in our equations. In our PMOS, we're actually using the voltage drop over resistor R1 is effectively what's happening here. So this is going to be equal to IDRS plus VSG, and now I'm in a place where I can easily do some algebra and figure out what ID is in terms of all that other stuff. So that's going to give me ID is equal to VDD R1 over R1 plus R2 minus VSG all times a factor of 1 over RS. I can then set this ID equation equal to my saturation region drain current equation. Donald, do I need to explain subscripts again? Did I write things poorly?
Is that an equal sign on the third equation at the bottom?
So this is VDD minus this guy. So I've just moved VG to the other side of the equal sign, where VG is VDD times R2 over R1 plus R2. Okay. So I moved VG over, and then I effectively just factored this guy where 1 minus R2 over R1 plus R2 is the same as R1 over R1 plus R2. So, excuse me. I can say that VDD times R1 over R1 plus R2 minus VSG is equal to 1/2 K sub P times RS times VSG minus the absolute value of VTH quantity squared, where K sub P is just the transconductance coefficient for our PMOS transistors, which is just mu P C ox W over L. So literally the exact same thing as K sub N that we used the other day, except that now we're using whole mobility. So this is extraordinarily similar to the equation that we developed when we were dealing with NMOS transistors, and skipping several steps of algebra because I'm sure you're all bored by it, we're going to wind up getting a result that says VSG is equal to the absolute value of VTH minus 1 over KPRS plus the square root of 1 over KPRS quantity squared plus twice, there's going to be 2 over KPRS multiplied by VDD times R1 over R1 plus R2 minus the absolute value of VTH is our answer. So again, we're going to have, we have a quadratic relationship. We're going to have two solutions. One of the solutions will always be negative. Since a negative number can't be greater than the absolute value of something else, the negative solution is obviously incorrect. This guy is the one that's going to give us our positive value for VSG, and it should always be more positive than the absolute value of VTH, implying that our device is on. From here, we could determine our drain current using our equation, and then we would simply need to compare this to the quantity VSD. So let's look at what VSD is going to be here. It should be fairly straightforward. So VDD, if we do KVL on the right-hand side, VDD is the voltage drop over resistor RS plus VSD plus the voltage drop over resistor RV, which means VSD is simply VDD minus RS plus RD times our drain current. All right, so KVL on the right-hand side. And we now have a means to determine whether or not the device is actually operating in the triode region or confirming the saturation region operation. So if this quantity VSD is greater than VSG minus the absolute value of VTH, we guessed correctly. If it isn't, it's in the triode region, and then we need to do our triode region analysis. So just like we saw with our NMOS transistors. Okay. For triode region operation, we can say that VSG is VDD minus IDRS minus VG, which simplifies to VDD times R1 over R1 plus R2 minus 1/2 K sub P. Sorry, not 1/2 because this is triode. My apologies. KP RS VSG minus the absolute value of VTH VSD minus 1/2 VSD quantity squared. So I've just plugged in the triode region drain current equation, excuse me. And we can say that VSD is VDD minus RS plus RD times ID, which becomes VDD minus KP RS plus RD times VSG minus VTH, VSD minus 1/2 VSD quantity squared. Solve these two guys to determine VSG and VSD. And then only one of the solutions will give you a situation in which the source drain voltage VSD is less than the overdrive voltage, meaning that the triode region operation is correct. All right. So with channel length modulation included, I'm not going to spend a whole hell of a lot of time doing this. We're literally going to take this equation here, substitute in our ID, this equation here, substitute in the correct ID, and that's going to give us our two equations. Solve those, determine whether or not it's working in saturation. Okay, so with channel length modulation, assuming saturation, the result of literally plugging in the saturation with channel length modulation value for ID into these two guys gives us the two equations. VSG is equal to VDD times R1 over R1 plus R2 minus 1/2 K sub P RS VSG minus the absolute value of VTH squared 1 plus lambda VSD. And our second equation is VSD is equal to VDD minus 1/2 KP RS plus RD. VSG minus the absolute value of VTH quantity squared 1 plus lambda VSD. All these two guys, and we're good to go. All right. So there is a self-biasing network for PMOS transistors, okay? But can I scroll up a little bit here? If we go to our self-biasing network schematic diagram, there's really not a whole hell of a lot of difference, right? So we should see that we get effectively the same equation, except that all of our VTHs should have absolute values. And I believe all of our KNs should be KPs. That's it. So I'm not going to go through, waste the effort of solving it again when it's an identical derivation. All right, so that's MOSFETs. I'm done. So much math. Yes. Sure.
Our test is a week away.
A week away. The material that will be on your exam stops today. Okay. So we're going to have BJTs and MOSFETs, just the theory behind how they work, and then DC biasing circuits in both cases. Luke, you were, okay. Andrew. I don't think so. I'm gonna set up a MathCAD sheet and work them with my calculator as well to try to make sure that you don't have to do any sort of hand iterations. But my expectation is it should follow The homework pretty much straightforward. I'm not going to ask you anything that I would say that your numerical solution problems, I'm definitely not going to ask you to solve anything unless it's really simple, like I give you what VBE or something has to be that makes you include early effects so that you don't have to do iteration of 3 different variables keeping up with each other, because that will take forever, as I'm sure some of you found out. So with regards to the kind of problems that I expect you to have to do some sort of numerical analysis on, it'll be things like, okay, I give you maybe 3 or 4 simple circuits with a bunch of voltages given, and you have to tell me which mode the things are operating in and prove why you say it's operating in saturation, forward active, or triode, depending. I'm mixing terms here because I'm not telling you whether or not it's going to be a MOSFET or a BJT, that kind of thing. And then just determining the DC operating point. So for your DC operating point questions, I mean, that could be 3 separate questions because I want to know both VCE, VBE, and the collector current. Or for a MOSFET, I'm going to want to know VDS, VGS, and ID. So I really do think doing the homework, at least the first part of the first 3 questions by hand would be good practice for what's expected of you on the exam. And then I'm going to get a MOSFET homework set up for you. I think tomorrow for sure. Definitely tomorrow. Maybe some of it today, but definitely tomorrow. So that you have roughly a week to work on those problems as well. And it'll be of a similar situation as your last homework, except just using MOSFET circuits. So with regards to numerical problems, what I've asked you to do on the homework is what I intend to ask of you on the exam, but my intention is to be slightly easier so that it doesn't take as long. I definitely won't make you rework the problem 5 different ways by making subtle variations to see what the hell happens when you change beta or the power supply voltage, for sure. We have not done any small signal analysis with MOSFETs or BJTs to this point, so there cannot be any small signal anything on your exam. So it's all of your numerical problems will be large signal DC biasing. Julia, I'd like to speak with you after class, actually. Yeah, no, I need your help with something. Yeah. Or I would actually, let me rephrase it. I would like your help with something if you're willing to give it. Yeah. Yes, so I'm going to get a homework uploaded. It takes me forever to make, so I use a program called, I think it's latex, something like that, to draw all of my circuit diagrams. And unfortunately for MOSFETs, they're very complicated. So it takes me forever to draw the picture. Once I get it, it's good to go. So yeah, so it's a pain in the butt for me to draw it, but as soon as I get that done, it'll be uploaded. The problem itself is just, I put resistor values in, I make sure that my math CAD sheet gives me an answer that I want it to have. So if I want you to go through the effort of saying, oh, it's not in saturation, now I have to do it in triode or not effectively. But yeah, so you'll definitely have a homework set up by the end of tomorrow.